Okay, so we are going to continue on with chapter 4. I'm checking a few things. Hang on just a second. Where's my settings? Oh, I can't fix it. Hopefully we're getting some sound here, just to be sure. This is notes 4.5. Our goal today is to identify a function's increasing or decreasing intervals using the derivative. Okay, so now what we've been working on for the past 4 days or whatever is finding the derivative algebraically. And now we're going to use that derivative to see where the derivative is positive or negative, and therefore tell what the original function is doing at those points. Okay, so there's kind of steps to this, and a lot of these steps are just AP steps where you have to show everything, but you also just want to think about these things as well. Okay, so we know from prior lessons that if a derivative is positive, then the original function must be increasing. And then if the derivative is negative, then the original function is decreasing. This goes back to our chart. So if f prime is greater than 0, then f must be increasing. And if f prime is less than 0, then f must be decreasing. Just like if v of t is greater than 0, then the position function must be increasing. Okay, so we're relating all of this together, but now with an algebraic undertone. So it has, for each function, we're going to state the domain, because remember, critical points only occur where the original function actually exists. So we're going to look at that first. We're going to find the derivative of the function, so its first derivative. We're going to find f prime algebraically. We're going to sketch the derivative graph or construct an f prime table, and I'll explain what that means. Okay, and then from this f prime table, we're going to have a table now that shows intervals where the function is positive versus negative on f prime. So therefore, we'll be able to answer where f is increasing or decreasing. Okay, so that's the overall goal. So we're going to try this first with a basic polynomial. Okay, first of all, think about its domain. So f's domain is all real. So I'm just going to kind of jot that here. We're going to go from negative infinity to infinity. It's a polynomial. It's a snake of some kind doing something funky in the middle, probably. Okay, we're going to find the first derivative. So f prime of x will be equal to, simple power rule, 3x squared minus 6. Then the plus 1 is constant, so that's gone. Okay, we're going to find that first derivative, and then it says sketch the derivative graph. I feel like there's a step missing here. To sketch the graph, what we kind of need to do is figure out where the first derivative equals 0 or does not exist. Let's find some critical points on this graph and identify them as such. So we're going to set f prime equal to 0, does not exist, and then we're going to say, well, that gives me 3x squared minus 6 equals 0. So 3x squared is 6, x squared is 2, so x is plus or minus the square root of 2. Okay, and then what they mean by constructing an f prime table is then at this point, we're going to kind of make a number line here, and on it I'm going to put negative square root of 2 and positive square root of 2. And I'm going to test values on f prime to determine whether f prime is positive or negative at these points. So if you're more of a numerical mind, you're going to want to test points. If you're more of a visual person, you could also think about this as a derivative graph. So if I were to graph y equals 3x squared minus 6, you should know that this is a parabola opening up, starting down 6, and there's no b value, so it does something like this. And I don't care what that actual vertex is. What I care about is where this function is positive and where this function is negative. And if I just look at this graph, this function is positive when I am to the left of negative square root of 2 and to the right of square root of 2, and it is negative or below the x-axis in between. So you could either do that, or you could have tested some points back here. So let's test a point on this interval, say 0. So that would be 3 times 0, which is 0, minus 6, which is negative. Check. Pick a number greater than the square root of 2. I don't know, 4. Any number bigger, 4. So 3 times 16 is 48, and 48 minus 6 is positive. Check. Negative 4, checking the other side, will give me a positive 16. 3 times 16 is 48, minus 6, boom, even function. Okay, so this is kind of that whole part C piece. And then finally it just says find the increasing intervals. Well, f prime is positive here and here, so therefore my increasing intervals are from negative infinity to negative square root of 2, and again from positive square root of 2 to positive infinity. And we're going to say because f prime is greater than 0. And then for part E, for my decreasing intervals, I will say that this function, oops, I'm sorry, go back. Put these in brackets because I'm answering increasing, decreasing. And then I'm going to say the same thing for E, but we're going to say from negative square root of 2 to positive square root of 2. And we're going to say since f prime is less than 0. And that's just a little justification statement. And that's it. Now, you could go back through and you could just look at that graph, but this is going to be a non-calculator problem. But if I just graph x to the third minus 6x plus 1, and I look and see what the graph is doing, let's just double check our values. So this is the original function. It's cubic. That's why my derivative was an x squared. It had a maximum, oh, still have f8 on. So that's why it has a maximum here, right? But the maximum is here on my derivative. Same thing over here for my positive square root of 2 value. So maybe not so easy to see and graph when I have something crazy like number 4, but we're going to do the same thing. So 4, again, find the domain. Now, think about this just for a second. I have something that is to the odd denominator power, which means that my function will be fine. It's just going to be flipped from one side versus the other over the origin so that it will be odd. What you'll need to kind of watch out for is just something to the even power here, because then you're going to take a square root or a fourth root, and then we can't have any negative values. But for our domain here, at least, this is all real. Find the derivative. So I'm going to label f prime of x is equal to 8/3 x to the 5/3 minus, and then we're going to drop this 2/3 down, so this is a lovely 50/3 x to the negative 1/3. And so we're going to, for part C, say f prime equals 0 or does not exist. I don't know what this graph looks like. I'm not going to have a calculator for it, so I can't do one of my fun f prime graphs. So I'm going to have to rely on a table. The problem is here, I've got to find the zeros first. So to find the zeros, we are going to factor. So we need to factor out, I guess, oh heavens, a 1/3 at least. Like, don't go crazy. Let's just get this in factored form and something that we can deal with. So I'm going to factor out a 1/3 x to the, and you always take the smallest exponent here. So my smallest exponent is an x to the negative 1/3. And then inside, we will be left with an 8x squared. Think about what happens here. This is 5/3 minus negative 1/3, which is 6/3. So that's squared, minus 50. And then I factored out the x to the negative 1/3, so it's just minus 50. Okay, and this is what I'm setting equal to 0. So to find the zeros, I'm going to set each one of these pieces equal to 0. So is it not true that if I have a 0 in my denominator, because that's what's going to happen here, my first derivative will not exist? Okay, so think about this. F prime does not exist at x equals 0. That's going to be a critical point here, because again, you could write it like this. and say that's the cube root of x there. Okay, so x is in my denominator, so can't be equal to 0. And then f prime equals 0 wherever this thing equals 0. Well, shoot, that's x squared equals 50/8, and then I'm going to take the square root of that. You would think I'd have an easier number here. The square root and the square root. So x is going to be plus or minus whatever the square root of 50/8 is. And I'm at a loss for that one. So if I have square root of 50/8, I don't know. Let's see. That would reduce. So that is the square root of 25/4. Okay, that's not that bad. Because that reduces. I was freaking out there for a second. But if I divide them both by 2, lo and behold, that's 25/4. And that is plus or minus 5/2. Phew. Much better than what I first anticipated. Okay. Couple notes on that. You probably could have factored out what a 2 up here, and if I had factored out a 2 here, this would have become more relevant at the start, but this is what I have. Okay, so now I have this piece. I'm going to go ahead and set up my f prime table, and I'm going to put all the places where f prime equals 0 or does not exist. So that's at -5/2, at 0, and at 5/2. Now we're just going to test points that are in between there into my f prime function. Remember, I'm trying to find where f prime is 0, does not exist, and then where f prime is positive or negative. So start putting in some points. But think wisely. I don't care what the actual value is. We're just looking for positive, negative stuff. So if I put in a 1, then here this quantity will be 8 times 1 minus 50, which is negative. And a 1 here will keep this positive. So that would be a negative when I multiply those two things together. If I want to substitute in over here a -1, -1 will give me, this will be a positive 8 minus 50. So this will be a negative. And then over here, this is going to be a negative as well. So I will have a negative times a negative, substituting in a -1, and that'll give me a positive. And then I have these two values over here. So now if I want to substitute in like a 5, pick a number that's not so bad. If I substitute in a positive 5, this part will be positive, positive 5. This part will be 8 times 25, which is 200 minus 50, which is positive. And if I substitute in a -5, this will still be negative, but this will be negative as well. Now, little hints, tricks of the trade. None of these zeros repeated. So none of these signs repeated, and they alternated all the way through. That kind of rule still holds true. Over here, my zeros didn't repeat, so we alternated signs all the way through. Okay, and what I mean by repeat is if that squared wasn't there, it was here, then those zeros would have repeated, so you would have seen repeating signs down here. Because basically after this point, we're finished. Because now we're just going to say our statements where the increasing intervals are where f prime is positive. So my increasing intervals are from -5/2 to 0 and from 5/2 to infinity, because f prime is greater than 0. And then E, we're going to say the decreasing intervals were from -infinity to -5/2 in union with 0 to 5/2, because f prime was less than 0. We're going to do this a lot. So look at the next one. Ooh, this looks like fun. Okay, how many pages do we have here today? Oh, goodness. Okay, let's do these two. So number 5, f is x times e to the -x squared. So the first thing we're going to do is talk about the domain. The domain of x is just all real. The domain of e to the whatever, unless the whatever happens to be some funky inside function, will also be all real. So check the domain of every inside and outside function, and we're all real. So this one is all real. Just keep that in mind. Okay, B, we're going to figure out where, what was step 2, was find the derivative. Okay, got it, f prime. This is going to be a product rule. So I have x, keep the first, times the derivative of the second. So the derivative of e to the anything is e to the anything times the derivative of the anything, which will be a negative 2x. Plus, because that's the first part of our product rule, now I'm going to take the derivative of x, which will be 1, and then I'm going to multiply that by e to the negative x squared. So that's the first times the derivative of the second plus the derivative of the first times the second. Okay? And now I'm going to clean this up before I start factoring. This first term here will be negative 2x squared e to the negative x squared, and then plus e to the negative x squared. So it's a lot easier to see that I'm going to factor out an e to the negative x squared, because our next goal is to set f prime of x equal to 0 or does not exist. So I'm going to say 0 is equal to e to the negative x squared times negative 2x squared plus 1. Find the zeros here. E to the whatever is never 0. Think about that. E by itself is going to be exponential growth or it's going to be exponential decay. This function never dips below the x-axis. So therefore, e to the anything on its domain will be positive. Has to be. Okay? So really all I'm doing is looking at this value right here, where that would be equal to 0. So I'm going to say that 1 equals 2x squared. That means a half equals x squared, and I'm going to take the square root of both sides. So x is plus or minus the square root of 1/2. A nice little tidbit about calculus, we don't care if you rationalize the denominator or not. So if you really, really want to, you can say this is the same thing as plus or minus square root of 2 over 2. But we in the AP world are perfectly fine with this as an answer. Okay, so now I have my 2 zeros, and that's all I really have. So I'm going to make my table, because I really don't know how this graphs, but I'll explain in a second. Okay, so here is my negative square root of 2 over 2. Here is my positive square root of 2 over 2. And then I'm going to look at my values here. My values don't repeat, so now you just have to kind of figure out what's going on. So plug in a 0, because 0 is easy. My hero, e to the 0 is 1, that's positive. Negative 2 times 0 is 0, plus 1, that's positive, this is positive. So that means everything on either side has to be negative. Done. Now, the other way that you can think about this visually is I don't care what's going on with this e and how that affects the graph. What I really care about are these signs here, because that will affect the graph. So just think for a second, if I were to graph negative 2x squared plus 1, I'd have to go up 1, and that's an upside down parabola. And so what happened? Here are my potential zeros. The graph is negative, then positive, then negative. Okay, so use that. E to the x is so easy in calculus. Like, just kind of throw it out the window. Like, it doesn't even matter sometimes. Okay, this is now my f prime. Now we answer the questions. So for part D, we know that f is increasing. I'm just going to write that out. From negative square root of 2 over 2 to positive square root of 2 over 2, because f prime is greater than 0. And then we know that f is decreasing on the other intervals from negative infinity to negative square root of 2 over 2, and again from positive square root of 2 over 2 to infinity, because f prime is less than 0. All right, let's do one more on this video. Then we'll all take a break. So number 6, I have x times the natural log of x. The domain of this, because x is not in absolute value, has to be x must be greater than 0. Please make sure that you are domaining it first, because if you try to answer an increasing interval where the function doesn't exist, that has to be wrong. Okay, it just has to be. Sorry. So my domain is x is greater than 0. Let's find my derivative. So I'm going to keep the first times the derivative of the second, which is 1 divided by x, plus the derivative of the first, which is 1, times the second, which is natural log. So I'm going to set this equal to 0 after I clean it up and say 1 plus natural log of x is what I got. So I'm going to say f prime equals 0 or does not exist. That's what I'm looking for. I'm spelling out what I'm doing. Algebraically, I could say I am looking for where the natural log of x is equal to -1. And that is at e, remember, e to the -1 will be equal to x. So that's my x value. The other way to think about that would be graphically, because before I do my table, you should pretty much know what 1 plus natural log of x looks like. Natural log of x is a inverted exponential growth or decay, and then it always has this point, and it does this, only we have moved it up 1, right? So instead of being there, it's just moved up 1, and now I'm here. The domain didn't change, just the location of this graph. Okay, so something is happening here. Well, here is e to the -1, which you recall is about 0.36. So this point is 0.36. And look what my function is doing. It is changing from negative to positive. So I'm going to graph my function here. My 0 is at e to the -1. We're going to make sure that we stop this at 0. That's where your domain is going to come in, so that you don't accidentally write anything below 0. And then just think about what's happening here. So this goes from a negative to a positive. Okay, substituting in some values here might be a little hard to see that this is going to be a negative piece. Like what do I substitute in? Do I substitute in 0.2? I don't know the natural log of 0.2. So it's really handy to know the graphs, because now I'm just going to answer the question. And it says f will be increasing. That says increasing from, I'm going to say from e to the -1 to infinity, because f prime is greater than 0. And f is decreasing from 0, a soft 0, because it wasn't included in the domain, to e to the -1, because f prime was less than 0. And again, with any of these, you can take that, go back, I mean, at least for now, right? Go ahead and substitute in x, natural log of x, look at the graph, and gosh, it's really hard to tell right there, isn't it? Oh, that's the derivative, so hang on. I'm going to zoom this in once. See that little curve right there? That's what we found. So this function, the original function, was decreasing until I get to e to the -1, and then it just started increasing again. And then this other value, I still have my y8 on, so you're seeing the graph of the derivative. Whoops, you can't see anything. There you go. Okay, so here was my original. It's decreasing till there, and now it's increasing, and here's my derivative graph there. Okay, so, and if you just wanted to test me, go ahead and calculate the 0 on that derivative function. And you will get 0.367, which is e to the -1. Okay, we got a couple more examples, so make sure you come back.